Good morning, July 17. Fateful day in a good way. Uh, well, my younger daughter was born uh, today. Well, some years ago. All right. Da 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 da. All right. Yep. ELEC 1013, network cabling, Fanshawe College, London, Ontario. Let's go. All right. So last time we looked at the uh, principles of operation of the fiber optics. And today we're going to take a look at the practical applications. So, what do we see here on the first screen? Oh, you know what? Here, there you go. Here's my laser, virtual laser. Uh, it looks like patch panel, but it's not the patch panel that we know so far. We have known so far. This is not a copper wiring patch panel. It is the fiber optics patch panel. So what you see here, they're couplers. You get the fiber optic strand terminated with the fiber optic connector plugged in from this side. And you have another fiber optic strand plugged in on this side, and this coupler couples those two connectors, and the communication happens. So just can you imagine how precise this has to be, since when we have when we have multi-mode fiber with the core, and the information, the signal travels through the core of the fiber optic line. It's 50 microns in diameter. So how precise does this have to be to align these two cores? Now, when it comes to single mode, the core diameter is about, well, it is 9 microns, but it can go as low to 5 microns. So the alignment of those two connectors through this coupler has to be, has to be quite precise. All right, so today we're going to talk about, among other things, we're going to talk about loose tube type of cable, tight buffer cable, and ribbon cable. And also we're going to not refresh, but touch on or expand on some of the ideas that we talked about last time. It's all tied together. All right, so here's a loose tube type of a cable. You could see, this is the cable that you see in, well, you could see outside installed, and it's connected to the FOSCs. Now, let me tell you what the FOSC is. All right, so once upon a time, when you drive, you're going to see utility poles. Oh, that's a red. Let's not get red. Let's get some other color here. Blue. You will see some of the utility poles. All right. And so on. And once in a while, you're going to see a barrel-like object. All right. And it has some kind of a perforated things, and there are different wires going in. And sometimes you're going to see, well, along with that, you're going to see a slack going here and somewhere like that. There's going to be a slack. And these are the fiber optic lines. This was the device I was asking about in the lab. Yes, the FOSC. FOSC, fiber optic splice closure. The idea of this slack, this is where all the splices that are happening. That's when we're doing this week the fusion splice during the labs. That's where all those, for the most part, that's where the fusion splices live, in those fosks. It has to be nicely sealed against the elements, and this is a thick wire or cable that looks like this. Yeah, that's the cable that's being outside. The idea of the fosk is to provide the splices. So some of the fiber optic line could be going 20 kilometers that way. Some other ones could be going 20 kilometers that way. And over here they meet and they're being spliced, routed, or whatnot. The idea of the slack is so that fosk can be taken off and loaded into a working van. All right, I think it's something like this here. There's a person. Okay. So this thing is taken off, loaded through the back here into the working van, and inside there's the whole lab with a table and splicing, fusion splicing equipment and whatnot, all the paraphernalia that is needed to do the work on these fosks. The idea is that the environment has to be nice, clean, and dry in order to open that, do the work, close it up, and hang it back up. So that's why we have the slack. All right. All right, PBT, polybutylene terephthalate. It's an artificial component, man-made, that is used to produce those materials here. That toughness. It looks like plastic. It sort of is. Now here, FRP stands for fiberglass reinforced plastic. All right. So loose tube. Here's the PBT material filled with thixotropic jelly compound. So we're talking about these here, these tubes. And over here, we have the optical fibers. Yeah, just about anything with poly in it is synthetic, yes. Now, the idea of the loose tube is that there are tubes in which the fiber optic strands are inserted and floating freely or loosely. So that's why we have loose tube cable. Okay. Everything else is a protection. Now, the thixotropic jelly compound is jelly that fills out, that's filling those tubes in which those fiber optic strands is, to provide extra protection. The idea, why is it that we need to have those in a loose tube configuration? Well, this thing is installed outside, and outside in the winter, the temperatures will be cold. In the summer, as we are experiencing now, the heat wave of 2025, temperatures can also go up quite a bit, from the high extreme to the low extreme in temperatures. And as all objects, physical objects, well, some of them to greater degree, some of them to lesser degree, they will expand and contract depending on what the temperature is. So if those fibers were packed tightly, if they expanded during the heat wave, the constraints of the tube could actually crush the fiber. So they have to have a lot of playroom here, so they're nice and comfortable there. As an extra protection, there's that thixotropic jelly that compensates within its own consistency the expansion and contraction as far as the heat goes, hot and cold temperatures. When things expand, this thing contracts. When things contract, this thing expands. Talking about the thixotropic jelly, and provides extra cushioning for those fiber optic strands. On top of that, well, inside here, you have something that's called a strength member, and it's also some kind of a poly synthetic material. Whereas that number 3, center strength member, FRP, fiberglass reinforced plastic. There you go. That gives us extra protection as far as achieving the right flexibility, the right amount of flexibility. Excuse me. So, well, to begin with, these cables are not flexible at all. Well, they do have some flexibility, but it's far from things are far from being called that they're flexible. On top of that, right here, number 6 is a core wrapping tape, water swallowable tape, or polyester tape. This is the water absorption material. You can't escape, as we're going to talk about things later during this presentation. Water gets everywhere. In fact, I don't care how you're going to seal the tubes or pipes that are going underground, there's going to be moisture condensation that is going to eventually turn into water being present in those pipes that are underneath the ground. Which makes it a little bit more difficult for the wire pulling, but things are possible. The high power compression compressors come in play when it comes to blowing out the water, and then you still have to be really careful, because if the pipe ends up underneath some kind of electrical panel, of course you should not be putting the compressed air on the other end to blow the water out, because you'll be just blowing the water onto the electrical panel. So because water gets everywhere and we want this thing to be nice and dry, is a very special type of a tape. Some time ago in those commercials at 2:00 in the morning, that you could see something that looked like pills, but they were napkins, right? So you think it looks like a candy type of a white candy pill, and you put it in water, and this thing expands into a nice, huge kind of a napkin. That type of it absorbs a lot of water. This thing can absorb a lot of water and still be intact. And it does the job. And of course, everything is protected by number 8. It's the outer protection jacket. And there's some specifications here. If you want to expand on the chemical knowledge of things, you can. So here's the terminology. But at this point, we don't care about the chemical composition of the jacket. Right now, we're talking about using fiber optic lines, or using the fiber optics and the signal properties and all that stuff. We do not need to know the type of wood that our desk is made out of in order to be able to work on that desk, to use it. Right? So the same analogy. Okay, here is what I was talking about, some more chemical references or chemistry references and structure references if you're interested. go ahead. Maybe you're going to become a famous kind of a chemist um, instead of a telecommunication specialist. All right. Thixotropic, here's the explanation for the thixotropic jelly that is in there. I'm not going to go into the details. Read it later on if you want. Expand your knowledge. You can always expand your knowledge if you wish. All right. So let's talk about the bread and butter of what we are talking about today. Loose tube cable, designed for harsh environmental conditions in the outdoors. Fiber strands, here's the fiber strands, floating loosely in the desired rugged tubes. This is the summary of what I was talking about. Material contraction and expansion due to temperature changes will not affect the fiber strands because they are in there loosely, so they have a lot of playroom. Right? Used mostly in the outdoor, long haul installations up to 120 kilometers. So this and of course, when it comes to that type of installation, you would not see multi-mode strands in this type of cable. It's going to be single mode strands because single mode can carry the signal quite a bit longer. And once you see the 120 kilometers limit, and of course, as I keep saying, when it comes to reading the fiber optic related literature, different sources are going to tell you different distances and whatnot. And somewhat specifications. It probably has something to do with when the study was done, what equipment, during which year, and things like that, right? And who did those experiments. Excuse me. Yeah, sorry about that. There was some sort of a large bang that I heard, and my heart just stopped because I didn't know what it was. Turned out that the draft decided to close the door, one of the doors, very rapidly. Okay, so back to the regular schedule. All right. This is what the FOSC looks like. Fiber optic splice closure. We do have one of those decommissioned units, and well, during the one of the labs, I already showed it to some group. I'm going to just remind me to show this thing to you, so you can actually touch things that are inside and make some sort of a reference to that. Now here, there's a bit of a link. A lot of people who do the installations, quite often they record themselves and put the information on YouTube. You can just type FOSC installation or FOSC splicing. You can put that on, I can type it in YouTube search, and you're going to see a bunch of people showing how things are done, because I'm not sure if they're bored or do they have that artistic type of a side to themselves that they want to express themselves. Interesting things. So that's going to give you some sort of a picture of what's happening and how with those FOSCs. Now, from the loose tube wire, we're going to enter the world of the tight buffered cable. As I said before, here is here's the core of the optical fiber. That's where the signal happens. Here is the cladding that surrounds the core. It clads the core. This is where the signal goes in the core. So I'm just going to maybe here, signal enters and it travels in the core. That's where the signal travels. Okay. Now, the signal travels because of something that's called a total internal reflection. We need to establish a total internal reflection inside the core, so the signal or the light pulses or light modes or beams, otherwise, reflect from the interface, and interface is the point where one medium is interfaced with the other. So here is one type of glass, here's the other type of glass. The core has a higher index of refraction, which means it slows the light more. Cladding slows down the light less. In that arrangement, so this core is also pure glass, but slightly made dirty, slightly doped with some impurities on purpose to slow down the light. And in that case, when you have the interface like that between one and the other medium, you're creating a mirror effect. So you're creating the total internal reflection. So the signal travels through the core. All right, so that's the quote unquote core of things. Okay. Everything else that comes after that, there could be a buffer, there could be some other jacketing, there could be some more protection. Everything else is a type of protection that this core and the cladding needs to stay safe, so to speak, not to get damaged. And in some cases, you want things to be nice and tough. So even if you drive over with the car, so that loose tube wire that we talked about, you can drive over with the car and it should be still okay. Some other ones, other cables are being run underwater, under the oceans, and they have to be protected from all kinds of things, including the shark bites. Yeah, I'm looking at the chat line. It says the only place you won't get moisture is a perfect vacuum. Yeah. Well, that perfect vacuum includes no moisture, because then it would be something. Perfect vacuum has nothing in it. So as soon as you get moisture, it's not vacuum anymore. So there you go. So everything else, depending on the type of need, we are dressing up. So here's the fiber optics. All right, well, the core in this multi-mode for the tight buffer will be 50 microns, 50 microns, surrounded or cladded by 120 microns cladding, then surrounded or coated with 250 microns jacket or buffer, and then more buffer, 900 microns, and then everything else. This here, the tight buffer tube is meant for flexibility. These cables are not being installed outside. They are the internal cables. With these, you will connect one communication closet with another communication closet, or IDF to MDF. And IDF stands for intermediate distribution frame, and MDF stands for main distribution frame. In a building, there could be one MDF, and there are multiple IDFs that are feeding it. And the IDFs would be placed strategically around the building in order to accomplish the proximity of no more than 300 feet of any wire that's run end to end. And then that whole communication closet or the intermediate frame will have something that's called a media converter that converts all the digital electronic or electric signals into the light pulses, and that media converter sends the information or the information combined to the main distribution frame through the fiber optics. So these are meant to be inside in a nice controlled environment. These are meant to be flexible enough so they could be routed inside the building. Some of those also are being used as patch cables, those fiber optic patch cables. So they obviously we're not going to make them so tough that they can withstand the outside environment because we are inside. So we don't need that water absorbing tape. We can pack them tightly. We don't need to have them in the loose tube configuration because we are not having any temperature changes, extreme temperature changes. What we need is an extra protection from bumping around and maybe touching with some tools accidentally and things like that. Although, as much as protection this one has, still, when you run fiber optic lines, you treat it with extra care, including if there's a wiring tray or cable tray, the fiber optic should be aside from all the other data wires on the other side of the tray, just so it's not being bothered by anything else. Because it's easy to create a microband with fiber optics, and microband means a signal is going to escape the fiber optics. So what do we have here from the outside? We have the outer jacket, and usually those are going to be either yellow, orange, or aqua colors. And depending on the jacket, there will be this kind of cable. Like for example, if you see a yellow jacket, that means these fibers are single mode. If it's an orange jacket, it is a single multi-mode. And if it's an aqua jacket, then it's also a multi-mode, but a newer cable. And we'll look at that later on. And here's an armored yarn. Quite often Kevlar is being used. Kevlar is, it feels like silk strands, but it's, when you try to cut it with scissors, it is going to give you some resistance. So it's kind of weird because it feels like it's really fragile until you try to damage that or do something to it, and it's going to give you some pretty good resistance. Kevlar, also some of the earlier bulletproof vests are packed with Kevlar. So that's how tough that thing is. And then here, of course, there's going to be some sort of a rip cord, and we know what rip cord purpose is basically to, when you pull it, it rips the insulation or the jacketing, so you can strip it in order to terminate whichever way you need. Come on. Tight buffered cable designed for indoor applications as opposed to outdoor. If you install this thing outdoor, this whole thing is going to absorb moisture, and winter comes, all these fibers are going to be crushed. Because the water is going to freeze. So indoor applications. Now I just put the brown color here because I didn't want to put any orange, aqua, or yellow, but you will not see a brown colored jacket with that. So I just wanted to remain neutral with that, right? So no cable gets offended. All right. Designed for indoor applications, fiber strands packed tightly within the armid yarn and wrapped with outer jacket. Way more. I'm just trying to pronounce two words at the same time. Way and more. Way more. More flexible than loose tube cable, but also it's more fragile. Used mostly indoors in LAN environment, just as I explained about 30 seconds ago. This would be tight buffer cable in the LAN environment, and this type is so there will be some wires that are going from connecting from closet to closet, and there will be long cables. And sometimes you're going to have that into configuration of a patch cord to patch things. So here's the patch panel for, okay, look, what can we see here? I kept talking to you about things like media converters. Look what is happening here. What could this one be? This device right here. I'm just drawing this kind of like a rectangle around. Look, here's a transmit, here's a receive strand for fiber optic. And also at the same time, we have a copper wiring plugged in to the same device. Well, I'll give you 10 seconds to get an educational or educated guess. Okay, nobody? All right. It is a media converter, one of the media converters. What does it do? It converts electrical signals into light pulses. It translates the electrical signal from Ethernet into the fiber optic light pulses. So over here, there's a rack with a bunch of media converters. There you go. That's one way of looking at the media converter. All right, now we are jumping into something that's called a ribbon cable. You could see there is, well, almost the same as loose tube, except the fiber optic strands are arranged in a little bit more organized way. So what did I say a couple of years ago here? I always say a couple of years, excuse me. A ribbon fiber optic cable is arranged into a strip, a bunch of strips. It's a convenient solution for space and weight problems. Right. If I'm trying to lose weight, I need to eat more fiber. Not that kind of fiber, not that kind of weight. Well, here's the idea. You can pack more fibers when you arrange those fiber strands this way, which means you can have more fibers per cable, which means in one cable, you're going to need that protection, all the protection that goes around it, and that weighs a lot. So you can have less cables for the same amount of fiber optic strands if you pack them in this kind of organized way. So make the ribbons. So a convenient solution for space and weight problems. So the cable ribbons are actually coated optical fibers placed side by side, encapsulated in mylar tape. You want to try and find what mylar tape is. Similar to a miniature version of the wire ribbons used in computer wiring. A single ribbon may contain 4, 8, or 12 optical fibers, right here. This one is 1, 2, 3, 4, 5, 6, 7, 8. Okay. And the ribbons can be stacked up to 22 high. So you can pack way more strands if you organize them. And you still get the same effect as the loose tube. Color codes, as far as the color coding of the ribbons, this is up to 24. Remember that one? Blue, orange, green, brown, slate, and there's white. Okay, so those fibers are being color coded in order to have an idea what you're holding at the other end. So blue, orange, green, brown, slate, white, and here's the red. Here's black, yellow, violet, rose, and aqua. up to 12. And up to 24, you still have the same colors, but with the black stripe around them, except for the black one, because you can't put a black stripe on the black wire, so it's kind of like white stripe on black. That's the only exception. And here is the color coding of the 24 fiber optic strands. Now, those were the fiber optic strands here. Now, let's talk about the jacket color of fiber optic lines. So here's the jacket color. Multimode OM1, OM2, OM3, and OS1, OM stands for optical multimode. 1, developed earlier than optical multimode. 2, with slightly different specifications. Maybe some things were improved. Some years goes by, and then the engineers came up with an even better cable, and they call it OM3. So that's how things are being done. Up to OM4 right now, and optical single mode 1, optical single mode 2. Here are the numbers. This is the core size, and this is the cladding size. These 100 by 140, not as much used in our everyday applications. 62 OM1, that was the way old wire that was developed. I'm not sure if it's still being used. OM1 is still around because glass does not corrode. So a lot of the installations that are fiber optic that are perfectly fine are the ones that maybe were installed in 1970s, still intact. So the OM1, optical multimode 1, one of the first ones was 62.5 by 125. So 62.5 core diameter and cladding 125 microns. And everything else since that, you can see the cladding is always 125 microns. And the multimode has since OM2 has changed, and that's the new standard. Yes, you can still get you can still get the 62.5 equipment to accommodate the older OM1 cables. But 50 microns, you go to a distributor, you get it off the shelf. 62.5, you might have to wait a couple days for a special order. Right? Jacket color. There is a non-military and military. We're going to concentrate on the non-military because if you end up in the military, you're going to get extensive, detailed training as far as anything else. But I just want you to know that things like that exist. All right. So you can see that multimode up to OM2 are going to be with the orange jacketing. Then the OM3 and OM4, the latest cables, they will have aqua color jacket, and the yellow cables, like for example, here, you can tell that these are single mode cables because now, whether it's single OS1 or OS2, we don't know just by the color because they're both yellow, but you can tell for sure this is a single mode wire or single mode wire fiber. Remember this table here when we were talking about the category cabling? Cat5e, Cat6, Cat7, look, they can have transfer speed up to 10 gigabytes, Cat7, 100 gigabytes per second. And over here, you can see that the maximum length doesn't go over 300 feet. In any case, However, there's that new cable that's on the market relatively for not long, and it's called Game Changer. It can give you the Cat 6 specifications up to 1,000 feet. All right. Here's the similar table for the fiber optics. How do we see that? Now, here's length, but this is, look, 2,000 or 1,500. That's not feet. That's meters. So from here to here, it's 2,000 meters, which means it's 2 kilometers. Now, transfer speed, 100 megabits per second. Look, 100 gigabits per second, 100 megabits per second. 1 gigabit, 100 megabits per second. That's Cat 5. Right, 100 megabits per second, OM2, that's going to give you up to 1.5 kilometers. Now, we're going quickly into 1 gigabit per second. And that is going to give you OM1 with 62.5 microns. 1 gigabit, OM3 and OM4 up to 1 kilometer. It's going to give you OM3, 800 meters. OM4 is going to give you 1 gigabit per second up to 1 kilometer. 10 gigabits per second, OM3 and OM4 only up to 500 meters, half a kilometer, and so on. Of course, different literature is going to give you different numbers sometimes. And over here, here's the blue thing, blue area. Don't forget about single mode, and that doesn't even compare to the multi-mode. It goes into hundreds of kilometers. Well, 100 kilometers is a typical distance that can be still covered without the need of re-amplification or repeating the signal. So here's this table compared to that table. That's how we read that. Single mode cable is a single strand of glass, relatively narrow diameter, 8.3 to 10 microns, usually 9. Usually it has one mode of transmission that propagates at the wavelengths of 1310, 1550. On that account, there will be little light reflection when the light passes through a single mode of fiber core. Mouthful, meaning ideally the light would travel in ideal straight line in a single mode. So in a single mode, there's one single beam travels in a straight line. In reality, it kind of waves a little bit, kind of grazes around the interface with the cladding. But for our purpose, we're considering that to be a straight line. Consequently, it will reduce the fiber attenuation, so a single mode, and optimize the speed of transmitting signals, meaning the transmission distance is the significant performance advantage of the single mode versus multi-mode fiber. Single mode fiber is usually used for long distance signal transmissions, although sometimes you can see it in LAN communications. Connectors. SC stands for standard connector or subscribers connector, depending on who you ask. We are listing this thing as a subscriber connector, and it's only standard duplex, and it's a standard duplex fiber optic connector with a square modeled plastic body and push-pull locking features. SC connectors are typically used in data communications, cable TV, and telephony environments. SC is a snap-on or snap-in connector, also with 2.5 millimeters ferrule. That's the ferrule that goes from front to the back, and that's when the mechanical splice happens when you enter with the with the fiber optic strand, and you're butting it against the other side of the ferrule. So the ferrule goes like that. So now it's on. Let's see here. It was the connector of standardized TIA 568A. These are the standards, but was not widely used at first because it was twice expensive as the ST, the old connector. Now it's only a bit more expensive, but much more common. It's snap-in connector that latches with the simple push-pull motion, da. Right. So that's what the SC connector looks like. Now, later on, the LC connector was developed. It's same thing. It serves the same purpose, except, well, what did we write here? LC is a small form factor connector that uses 1.25 instead of 2.5 millimeter ferrule, which is not, here's the ferrule, half size of the SC. Here's the key component, half size of that. And it's standard ceramic ferrule. Ceramic ferrule is ceramic, which means it can attract static electricity, which means it can attract dust. So you gotta be really careful not leaving that thing uncovered. There's a cap. You should always have it capped. All those ferrules should be capped when not used. Good performance, highly favored for a single mode or a multi-mode as well. Also, what I've seen is in large data centers, when a lot of these connectors need to be put in, if you have a half size connector, it actually makes a huge difference when you're dealing with thousands of those connectors. At the end of the day, so to speak, the space, saving of the space, the room, how many equipment racks you have to have there. If you just one or two or 10 or 100, no, that is not going to make a difference. But if you're talking about thousands connectors in one room, the size of that is going to make a difference. You're going to have more connectors, more lines run in the same equipment environment. This is the old ST connector that looks old. Looks like the BNC connector that you use for your oscilloscope probes. Similar, like it looks. Now, let's talk about the wavelengths before we go. Typical wavelengths. Well, it's common to use frequency in hertz to specify transmission bands in radio communications. Optical fiber communication is set to use wavelengths. It's just the way things are. Can you use frequencies? Sure, you can, but we're talking about wavelengths in nanometers. Now, here's the interesting thing. Typical wavelengths for fiber optic communications. Optical communication relies on transmitting the signal in the form of light through a translucent medium, which is glass, sometimes plastic, but we're talking about glass. Ideally, the scenario would seem as following. Shine the light through the glass rod and receive it on the other end. In reality, the efficiency of the transmission is related to the wavelength of the light. So the wavelength of the light makes a difference. For the transmission to be most efficient, it needs to bear the least amount of obstacles, such as attenuation. Attenuation works against us. Scattering of light works against us. And believe it or not, absorption. What is scattering? Scattering. The light hits some kind of particle that is in the glass and it scatters, which means the light is being lost. Excuse me. Now, here is the scattering effect. The attenuation scattering, and absorption in one graph. Here are the wavelengths: 850 nanometers, 1300 nanometers, 1550 nanometers. Scattering is worst towards this end. And when we get to the higher frequencies, which would be lower frequencies, which would be longer wavelengths, the scattering is not as much a problem. With these wavelengths, the scattering is a lot of problem. Now, here's those two, nipples that produce absorption. What's absorption? The light is just absorbed by the medium and it just disappears. So you see here is 850 typical wavelengths of transmission, because here scattering is still there, but it's bearable. 1300, the scattering is even less, so that's better for us. And over here, 1550, the scattering of light is pretty much minimal comparing to that side here. So yeah, that's where we want to be. Now over here, you don't want to use the frequencies or the wavelengths between 850 and 1300, because this here, there is a peak of absorption. You have that light in this area here, in this wavelength, it is not going to get through the other end. It's just going to be completely absorbed. By what? By the water particles that are trapped during the production of the fiber optics. You can't escape. You're always going to have some water. Excuse me. Particles. So that's why these here, this one and that one, they're called water bands. Because the water absorbs these wavelengths. Light will not go on the other end with the absorption being this high. So that's why we can't just have anywhere as far as the typical transmission wavelengths. 850, 1300, 1550 are the typical wavelengths for fiber optic transmission. Now, attenuation, what is it? In optical fiber, the signal attenuates. It's attenuated because it covers certain distance and it gets tired of traveling after a while. It gets weaker and weaker and weaker. Attenuation. Signal weakens due to the length of the cable. Works with electricity and works with the light as well. Scattering. See the blue dotted line right here. We talked about that. And that's what scattering is. And here's the absorption. Absorption loss happens when the light gets locked in by the water molecules that are unintentionally trapped in the optical fiber during the production process. See the green peaks, these two, yeah, marked on the top graph. Regions under these peaks are called water bands because water is of those water particles are absorbing the light. Transmission using the wavelengths under these regions should be avoided because it's not going to happen. Typically, water peaks occur at 950 nanometers, 1380, and 2730 nanometers. More info if you want. However, there's always but. All right. As technology progresses, the fiber optic industry is implementing RWPF and ZWPF. What are these? Reduced water peak and zero water peak fiber. And those are considered full spectrum transmission lines. Yes, the engineers were able to develop optical fibers that do not have those water bands. And these are called full spectrum, right? Now, optical fiber primary transmission lengths, we talked about that. It's a summary. Here is the graph. Absorption, scattering, attenuation, wavelengths in nanometers. Industry implemented typical wavelengths, plastic optical fiber, usually used in connecting stereo equipment or in the car industry as well, to connect modules inside the car. Now, multimode and graded index. I explained to you already what graded index fiber optic line is. Just as a review, a graded index, just bear with me. If you have to go and catch the last couple minutes later on. Where's my board? Here. Just as a reminder, as a review, what graded index? It works only with multi-mode. So here is the core, and here is the cladding, and that's how things work. That's where the light travels here, okay? So if you look at that just from the side, here is the cladding, here is the core, okay? The light travels in different modes because it's a multi-mode. So some of the light modes or beams are going to travel in a straight line. Some of them are going to go under different angle and reflect from the core and get here. Some of them are going to be the even greater angle, and so on. So obviously the one mode that happens straight, that light is going to get the fastest to the other end. And any other modes are going to take longer distance to travel, and they're going to arrive slightly later. So as a result of which you get the dispersion. When you have a nice and sharp signal on one end, at the other end, you're going to have kind of dispersed signal. So that is going to affect the frequencies you can use, right? How fast you can transmit those light pulses. So what happens is that graded index is implemented, that if it's a graded index fiber, the core of the in the middle is constructed a little bit different. So the core is kind of not consistent. In the middle, the core will have the greatest index of refraction to slow things down, because if you slow that down and let the others catch up at the destination, then you're going to end up with a sharper pulse at the other end. So in the middle, the index of refraction is the greatest. As you travel towards the outside of the core, the index grades into a little bit less and less and less. So that's what they mean by graded index, multimode graded index. So typically typical wavelengths for the multimode and graded index would be 850 nanometers and 1300 nanometers. And for the single mode, typical wavelengths would be 1310, 1490 to 1625, and 1550 being the typical wavelengths that can be transmitted. And that's the end for today. So that concludes the 2-lesson unit on the fiber optics that we're covering. Anything else that we're going to do, we're going to reinforce that knowledge with the practical labs activities. And we are already doing the fusion splicing during this week. And week 13, I'm going to introduce you to the mechanical splice as well, because I want you to be able to do both. All right. Of course, when you get hired in the industry, you're going to get different type of equipment. Everywhere you go is going to be different type of equipment, but the basics of operations are going to be the same. You're just going to have to learn how to press different buttons to accomplish the same things. All right. Thank you so much. You guys are wonderful, and have a great weekend. If I don't see you, and I'll see you when I see you next week.